In this fourth and last episode, we are going to use substitution method to evaluate indefinite integrals involving exponential functions and integrals that will lead to logarithmic functions. So let's recall the substitution method. We have integral of f of g of x multiplied by g prime of x dx. This is equal to integral of f of u du, where we have used the substitution u is equal to g of x. We will also list two important rules, and the first one is integral of e to the u du. This will be the same as e to the u plus c. And the second one is integral of du divided by u. This will be equal to ln of absolute value of u plus c. Let's try the first example. For letter A, we have integral of 2x plus 3 times e raised to x squared plus 3x minus 5 dx. Recall our formula that integral of e to the u du is equal to e to the u plus the constant c. Example A is not yet in the right form, but if we do the substitution u, which is the power of e, x squared plus 3x minus 5, and take the derivative on both sides, so this would be 2x plus 3 dx. Notice here that 2x plus 3 times dx is exactly this right side, which is just du. Now we can rewrite this integral now as integral of e. That power now becomes u times 2x plus 3 times dx, which is just actually du. Now this is exactly the same form as our formula. So evaluating this integral, we will have e to the u plus c. Now after this, we can just replace the u, which is x squared plus 3x minus 5, and we will just attach the c. And that is our answer. For letter B, we have integral of e raised to the square root of x divided by square root of x dx. As before, let us let u to be the power of the exponential, which is square root of x. Note that square root of x is just x raised to 1/2. And if you take the derivative on the left side, this will be du. The derivative of x raised to 1/2, the 1/2 will go down. This will be x raised to 1/2 minus 1 dx. Or we can rewrite this as 1/2 x raised to 1/2 minus 1 is minus 1/2 dx. Or we will get du is equals to 1 over 2 square root of x dx. Now in our given, we have dx divided by square root of x. So we have here dx divided by square root of x. We do not need the 2. We can multiply both sides by 2. So we'll have 2 du is equal to 1 over square root of x dx. Using this information now, we can rewrite our integral as integral of e to the u times dx divided by square root of x is actually 2 du. Moving now the constant 2 outside of the integral, we will have 2 of the integral of e to the u du. And using the formula, we will have 2 multiplied by e to the u plus c. Replacing now our u, which is square root of x. This will be our final answer. For our second example, we will have exponential combined with trigonometric functions. So for letter A, we have integral of sine of 2x multiplied by e raised to 3 plus cosine 2x dx. As before, let us let u to be the power of the exponential. So this will be 3 plus cosine 2x. And we have du now equals to derivative of 3 is just 0. Derivative of cosine is just minus sine 2x times the 2, because we have to use chain rule here, dx. What we need here is sine 2x dx. We do not need the 2, we do not need the negative. So we divide by negative 2 both sides. So we'll have du divided by negative 2 equal to sine of 2x dx. Using this information now, we can rewrite this integral as e to the power now will be u times sine of 2x dx is actually du over negative 2. We can move negative 1/2 outside of the integral. So this will be integral of e to the u du. And recall our formula. Integral of e to the u du is just e to the u plus c. So we will now have minus 1/2 e to the u plus c. But this will be just minus 1/2 e raised to, our u is 3 plus cosine 2x, and then we'll attach the c. For letter B, we have integral of sine theta divided by 1 minus cosine theta d theta. If we let u to be 1 minus cosine theta, then du will be derivative of 1 is 0, derivative of cosine is negative sine, but times a negative, this will be positive sine theta d theta. And we have sine theta d theta in our numerator. So this will now be integral of du divided by u. Recall the rule that says integral of du over u is equal to ln of the absolute value of u plus c. So in our case, we will have ln of u plus c. Finally, we will have ln of absolute value of u, where u is 1 minus cosine theta, and then we copy the c. For our third example, letter A, we have integral of 3x to the 5th power divided by x raised to 6 plus 1 dx. You have seen this many times that when we choose the u, its derivative must be present in the integral. So if we choose u to be x to the 6 plus 1, then du will be 5th power, which is in our numerator. So the derivative of x to the 6 is just 6x raised to 5 dx. But this is not exactly what we want, because this is 3x to the 5th power. So that means we can divide both sides by 2, and we have du over 2 equals to 3x to the 5th power dx, which is exactly what we need. Now rewriting this integral, we will get integral of du over 2 divided by u. But this will be equal to 1/2. We can move the 1/2 outside the integral of du over u. And using now this rule, we will get 1/2 of the ln of absolute value of u plus c. Replacing now the u, this will be ln of x to the 6th plus 1 plus c. We can keep this as our answer, or we can remove the absolute value because x to the 6th plus 1 is a positive number. For our last example, we will have integral of cotangent x dx. We can rewrite this integral as cosine x divided by sine x dx, because cotangent x is cosine x divided by sine x. And we will just let u to be the denominator, which is sine x. And its derivative here will just be cosine x dx, which is exactly our numerator. So this will be integral of du divided by u. And again, using this rule, you will have ln of the absolute value of u plus c. Now replacing the u, which is sine x, and attaching the c, that will give us the final answer.